everyone, welcome back to our Calculus 2 course. Today I'm going to cover two sections of chapter 6, section 6.4 and 6.5. You guys are going to see some applications in physics, I think, using calculus. Let's start with section 6.4. It's about work. And then on 6.5 we'll be talking about the average functions, the intermediate value theorem. Okay? So 6.4 we talk about force. Okay, and then work. And you see the word force, right? So force is denoted by F, mass times acceleration. Okay, so you recall we have a constant. It's gravity. G is acceleration due to gravity is at 9.8 meters per second square, I think, and A here in general. And in here I'm using metric units. Okay, but you may have empirical using pounds and miles. Make sure that all the units match up. And then we're going to talk about the spring. Well, something like this called spring. Okay? Or maybe this way, horizontal spring. And the force associated with the spring is K times X, where K is a constant. Now, by the way, this is from the Hooke's law. I took physics a while ago. And X is the distance from its rest position. So each spring going to have its natural length. So it's right there, it's resting. Nothing happened, right? If you use some force, say to pull the object away from its resting position, you're going to need some work to do so, okay? And you got to use some force. And the force is calculated by K times X, depends on how far you pull or push or compress the spring. You're going to need more force. Okay? And after that, you're going to have something called the work. It's energy. Work is equal to force times the distance that you move. Okay? The farther you move, the greater the force you apply. You're going to spend more energy. Right? So that's the whole idea for 6.4. So let me just start showing you some examples, and you will have some idea of how to apply calculus into some application subject, and here is physically. Okay, so I see the first example. We have a spring. Okay, and the very first thing, whenever you do apply math into some applications, in here we better choose our coordinate system. And usually we choose x-axis right at the resting position. So 0 is right here. It means what? I don't need to use any force to have the object right there. See, the spring is at rest, and I don't need to use any work at all, because if the force is 0 times whatever, the work is 0. No energy needed. And if I move further away, and this is example 3 in the book, say what? I'm going to need a force of 40 Newton to move the spring from its resting position to, which is 10 centimeter long. It's from here to here is 10 centimeter. Okay, and I'm going to move this further. We get 15 centimeter. So how far did I move? 5 centimeter. Okay. Oh, by the way, we should not use centimeters when we do the work. We have to convert back to meters. So how far did we move? 5 centimeter, which is 0.05. Is that right? 5 centimeters. Yeah, 0.05 meters. So this is gonna be 0.05, and it's gonna take 40 Newton force to move the object from 0 to 0.05 meters. Okay. And then the question asks us, how much work do we need to move the object from right here? Now it's right here. 15 centimeter long to 18. So in other words, we want to move it another 3 centimeter. Okay, so this is going to be 0.08. And what is the work needed? Imagine as a rest right here, right? We spend 40 Newton of force to move it right here. Now it's right there. And they ask us, this is the force, not the work, okay? And they ask us how much energy needed, or how much work do we need to move the object from here to there. This is 0.08. And what's the question? Okay, so let's try to work on the problem. First of all, it's a spring, so I gotta bring up the Hooke's law, force formula. K times X. And I know that the force that I need to move is 40 Newton to move from its resting position, which is 0, all the way to 0.05 meter long. So K is a constant, and the distance that I move is 0.05, I think, right? I have to change the meters, okay? So K, of course, easy to calculate, 40 over 0.05, which is, I think it's 4,000 over 5, so 800. It's the constant. So my force function is going to be 800x, you see? The further I move, the 800x. The greater the x, the more force that I will need. Okay, so 0 is right here. I move further, I need more force. So from here, if I move a little bit more, say from 0.5 to 0.6, I'm gonna need some more force, right? And then from 0.6 to 0.7, the x is gonna be bigger as 0.7, so it's gonna have more force. And I add all the force together. And I take the force times the distance, I have the little work that I move, okay? And I add all the little work together, I have the entire work needed. Okay, so we are right here. We move a little bit further, say move dx, so the little work that needed to move the object from here to a little bit further is force times a little bit distance, which is 800x times dx, okay? And then you add all the little force together. Hopefully you guys are with me so far. The object dimension is right here, okay? And if we move a little bit further, we move a distance of dx. We're going to apply the force times dx. We have the work done. And the force is going to be changing because x now is changing. Okay? X changed from 0.05 all the way to 0.08. Force times the distance is the work. And the force times the little distance, you have the little work. You want to calculate the entire work that you need to move the object from 0.05 to 0.08. You add all the little force together, okay, which is the sum of all 800x dx, and x run from 0.05 all the way to 0.08. Then you calculate this. You have the amount of work needed to move from here to there. Okay. Say, what if they ask you a question? Now you're right here, and you want to move the object from 0.08 all the way to, say, 0.1. 0.1 is right here. 0.1. Then what? You do the integral 800x dx from 0.08 to 0.1, and you have the force. I'm sorry, you have the work needed to move the object from here 2 centimeters further. Okay. That was the idea. That is for the horizontal spring that needed. And by the way, keep in mind that you have no friction at all. Okay, assuming that this is no friction. If you have friction, the problem is going to be more complicated. You have to calculate the factor of friction involved into the game. Okay, but we make it easy, no friction. Now, second example. I see that we have a building, okay, and there's a rope all the way down here, and you are right there, and you want to pull the rope up to the top of the building. Question is, how much work needed? Okay, again, one more time, we got to collect information. The first thing I'm going to do is to choose the coordinate system, okay, to the x-axis going this way. This is 0 right here, this is x-axis. And they gave us the length of the rope is how far? 100 feet. So if 100 feet, at this point going to be 100. Oh boy, it's feet. Okay, it's not meters. So we have to use vertical feet and what pounds. All right. And what is the weight of the rope? It's gonna be they call it cable. Okay, the cable. The weight of the cable is 200 pounds. 200 pounds. And the length is 100. One thing that I didn't see in here, but I have to mention is when we have to assume that the density of the roof is the same. Means when the weight is equally distributed everywhere on the rope. Not the case that this part of the rope of the cable going to be heavier than the other part of the cable, which happened in reality. But we have a very ideal, perfect cable, perfect rope that have identical density everywhere. And of course, 200 pounds out of 100 feet long. So the density is, let's go by density. It's 200 divided by 100. This is density. Okay, is equal to 2 pounds per foot. Okay, each foot in average is weighed about 2 pounds. Okay, so that's the information I got, and I have to use some force, right? I have to spend some energy, some work to pull the cable all the way from down here up there. The thing is, the cable have weight, so it's not the same amount of energy that same amount of force that I will use to pull the entire cable up. So if I chop it up into many pieces, and say this piece is right here, okay, it have same weight, but I only need to move this distance, shorter distance, so I will need less energy or less work. But this pipe right here, even though it's the same amount of weight, same weight, but I need to move a longer distance, so it's going to take me more work. Okay, and like I mentioned before, whenever you want to have this problem like this, you want to use calculus. The idea is what you try to chop it up to many little pieces, and you calculate a little quantity at a time. In this case, we're going to calculate the work needed to move a little piece of that cable at a time. So in other words, imagine that I'm chopping that cable up into many small pieces, and I'm going to calculate the work I need to move one little piece up. See how far? Okay, so if I chop it off right here, that little piece is at the position X. See why I choose 0 right here? So X is the same thing at the distance that I need to move. So the little force that I need to move that little piece of cable from the position X all the way up is the force times the distance B, right? B now is equal to X. B is the distance from here to here, which is the same thing as X in this case. Okay, and what about the force? Oh boy, here. We have the density, right? 2 pounds per foot. And then the length of that little piece is dx. So 2 times dx will be the weight of that, weight is the force right here, of that little piece of the cable or the rope. So dW, this is the force by the way, okay, is 2 times dx and then times x for the distance, okay. This is a force, and this is the distance, okay. You take the force times the distance, you're going to have the weight. And you see this, the distance is changing. If that piece of the cable is far away from the top, then the distance is going to be longer, right? That piece of the cable closer to the top, then the distance d is going to be shorter. Another x is going to change. And you can see what later on I can tell. I can do the integral from 0 to 100 because the distance is going to vary from 0 to 100. And the force needed to bring that up, the weight is 2 times dx because the density is the same. So we use the same amount of force. Okay, so this is my EW. So my entire work needed is total of all the little work, which is integral of 2x dx. I'm just rearrange the term, right? I move the x all the way to the right and then x in the middle. And the next one from 0 to, I think, 100, okay, you integrate it. And the units is going to be in terms of feet times pound, okay? It's not joule anymore. Integrate it. You have the answer. Okay. Next, move on to another example. Let me see the picture in here. All right, I see a tank of water. What I have. It's a tank. The radius, say right here. The radius is 4 meters. Yes, 4 meters radius. Okay. The height of the tank is 10 meters. From here to here is 10 meters. Okay. And I see that we have some liquid up to here. of the tank, the distance from top of the tank to the surface of the liquid is 2 meters. Okay. It's water, right? And they ask you what? Find the work required to empty the tank by pumping up. Okay. So your job is to take out all the water out of the top of the tank. Okay. That was the idea. I can draw that. This is the center line. Okay. So the idea, again, one more time, is to apply calculus. The idea is what? We chop it up. That's this water right here. We're gonna chop it up into one slice of water. And we're going to bring that much of the water, one slide, all the way up, okay? And then another slide right here, smaller slide, okay? So the weight going to be different, the force going to be different. We move it all up, and every single slide of water, we're going to use a dW amount of force, amount of work, okay? A little amount of work. We add all the little amount of work that we spend on it, we have the entire amount of work that needed, okay? Again, to do this, apply math, we better choose our coordinate system. Some people may choose the origin right here. Some people may choose the origin right here, right at the surface. It doesn't matter, just choose one. And you're going to calculate the math based on your coordinate. I'll choose right here, okay? So my x-axis right here, 0 right here. So this point right here is going to be at 2. The point right there is going to be at 10, okay? And the unit is meters, so it's awesome. We don't have to change anything. Okay, so we want to calculate the amount of work to bring one slice of water all the way to the top. And that dW, little amount of work, is F times D. Is that right? So we have to calculate D. So if the slice right here, let's call it X because it's variable changing. So X is going to be changing from where to where? From 2 all the way to 10, right? So if the first slide is going to be at 2, you have to move that slide up. And the last slide, which is just one little dot right here, you have to move all the way up here. So X here is going to change from 1 to 10. I'm sorry, 2 to 10. And D here is equal to, oh, D is ugly. D here, the distance you move, that's like the depth is what? From, is X is 2 less than or equal to F less than or equal to 10. That's what I got. So I know that my integral is going to be somewhere from 2 to 10. All right, so D is that much. What about the force F? I know D already. F now is going to be, what was that? Mass times acceleration, right? Now we'll go against the gravity, so this is going to be mass times G. Meter right here, so the G is okay, 9.8 something. And how do I calculate the mass of that slide of water? Mass is, let me see if they give us density in here. Oh, density is given. The density is usually in physics, you know, by rho. It's called rho. Okay. It's equal to 1,000 kilogram per meter cube. Okay. And we have mass is equal to the density times the volume, yeah, right? It's physics in here, so if you have some background physics, that'd be easier. If not, just trust me on this, okay? The density times the volume is going to give you the mass. This is the density right here times the volume, yes? Okay? So density is given. Now you have to calculate the volume of that little disc right here, that little slice of water, okay? Because this is mass, okay? This is mass. Okay. I want to calculate the mass. I know that rho times volume, this rho, the density is given 1,000 already. So how do I calculate the volume? The volume of that little disc, the thickness is dx, right? Because I chop it up very small. And then the area times the thickness, then you're going to have the volume of that disc, right? See, I have a disc right here, look like this. Okay. And I want to calculate, I chop it up right here. The volume, I'll have to calculate what? The radius, okay? I have the radius times the area is going to be pi r squared radius squared times pi. You have the area and times the thickness. So the volume is pi r squared times the thickness, which is dx. Okay. So it's down to calculate the area, the radius of that little disc right here. Okay. Now I have to use another geometry in here. See what I got. Okay. This is 4. This triangle that I'm looking at. Okay. And from here to here is 10. This is 4, and this is 10. And if I have r right here, I chop it up this way. This is r. Okay. I'll write 10 down here. From here to here is x. Okay. And this is r. Can I write r as a function of x? Use similar triangle. 4 over 10. This one over that one. Okay. A bigger triangle is equal to r over 10 minus x. I'm talking about this smaller triangle right here. This is x. So this height down here is 10 minus x. And then from here to here is x. And then from here all the way down here is 10. You guys with me? So this little triangle right here is going to be similar to the bigger triangle. Okay? So r here over 10 minus x, r over 10 minus x is going to be equal to 4 over 10, which is 2 over 5. So r is 2 over 5. So r is equal to what? 2 times 10 minus x over 5. So I'm going to have the volume. I think it's okay to erase this. I have some room to write. The volume of that little disc is, it's called little volume. Little volume is pi r squared times dx, which is pi 2 times 10 minus x over 5 squared and then dx. Okay? So the little mass, okay, it's gonna be F here is m times g, which is mass is rho times v times g, which is 1,000, and v right here is pi. Let me do the math here, make it easy. So 4, 10 minus x squared over 25. Then dx, right? That's the little force, so I should put like a df right here, if that makes sense. Little force needed, okay? The little force is a little mass times v, and the little mass is rho times little v. Okay. And then what? This is the little force in here, and then I gotta multiply by x right here. So what? The little work is equal to little force times the distance, which is what? Little force times d, which is x. So look at everything in here. You have what? A little force. Little work unit is 1,000 times pi times 4, 10 minus x squared over 25 times dx, and then times dx with a distance. The whole thing, and then times x, right? Then let's rearrange the term, and then the total force is the sum of all the little force. I keep saying force, no force. This is the work. The total work, the total energy is the sum of all the little energy. I'm going to put all the constant outside, so pi outside, 4 outside, 1,000 outside, and divide by 25 outside. Integral, what? 10 minus x squared is d here, it says x already. You know that d is x. And then times x, dx, and the x run from 2 to 10, as we mentioned before. And then you simplify this number. It's 1,000 times 4 is 4,000, divided by 10, 25, 105 by 4. This force is 160, I think. And then integral from 2 to 10 of 10 minus x times x, 10 minus square times x dx. And this is integral. Okay. So the integration itself is not really hard, but the hardest part is how to convert a physics problem back into the math equation. That's the hardest part. And hopefully that will be helpful. Okay? And this is the last example I cover on 6.4. Let me move on to the next section, 6.5. Is pretty simple. There's only one thing. The average value of a function